Hey guys, so today I'm going to be doing my curve sketching assignment. So in this assignment, I'll be going over how to sketch two functions. So the first function that we're going to look at is f of x is equal to negative x to the 3 plus 6x to the 2 minus 9x. So in order to figure out how to do this question, we have to look at the x and y intercept, the asymptotes, the intervals of increase and decrease, the local maxima and minimum of f, intervals where f is concave up and down, and the inflection points. And we can use all that information to sketch the curve. So on to the next idea. So we're going to be looking at the x and y intercepts. So for this, it is pretty straightforward. Since this is a power function, we can use this information to factor it basically and find what the x-intercepts are. So firstly, we can factor out the negative x from each of the terms since that is a common factor. And then as a result, we have x as one of our factors, and then we have a quadratic equation that we can factor further. Since this is a perfect square, this would be equal to x minus 3 squared. So as a result, we can use this information. Since this is equal to 0, we could set this equal to 0 and then find the x-intercepts of the graph. So we know that x is equal to 0, which is also the y-intercept as well. And we also know that x is also equal to 3, 0, which is another x-intercept. So we can plot these points on a graph. So as we can see here, the graph would go through 0, 0, and then it would also touch 3, 0 as well on the graph. So next, since we know that this is a power function, we can basically disregard the asymptote function because it's not rational. So we know that there are no vertical or horizontal asymptotes. So next, we're just going to look at the intervals of increase and decrease for the function. So as we can see here, the function that we have here is minus x, 3 plus 6x, 2 plus 9x, minus 9x, I mean. So what we do here to find the intervals of increase and decrease is we just take the derivative. So the first derivative of f of x would be f prime x, and we find that by using the power rule. So this is pretty straightforward. It'd be minus 3x squared plus 12x minus 9. So in order to find the critical points of increasing and decreasing where it changes, we just find the zeros of the derivative. So we basically just make it equal to 0 and then use quadratic factoring to find out what the numbers are. So we can factor out a minus 3 before factoring it into x minus 3 and x minus 1. So as a result, we know that since x and are the two factors, and we know that x minus 3 must equal to 0 and x minus 1 should also equal to 0. So as a result, we know that x is equal to 3 and x is equal to 1. So those are the critical points for the increase and decrease. So we can then use a table for this. So we basically just put the intervals. So when x is less than 1, x is in between 1 and 3, and x is bigger than 3. So by looking at a random point in that interval, we could see if the f of x is increasing, decreasing on that interval. So if it's negative, if the derivative is negative, as you can see for x is less than 1, we can see that it's decreasing, then it's increasing in between 1 and 3, then decreasing again when it's larger than 3. So as a result, we know that there's a local min at x equals to 1 and a local max at x equals to 3. Furthermore, we could then use these points to sub into the original function that we have to get the real points that we have. So we know that when x is equal to 1, the point would be minus 4, and when x is equal to 3, the max would be at 0. So we can then use this information to plot this on the graph. So you could see here that we not only have our x and y intercepts, but we also have the local max and min. So the max, like coincidentally, is also the same as the x-intercept at 3, 0, and then the min is at 1, negative 4. So by using arrows to represent it, we could generally see the overall shape of the graph already, where it's decreasing from all the way to 1 and then increasing, then decreasing again. So next we find the concavity up and down of the function. So basically what we do here is use the second derivative to get this information. So at this point, so we have the first derivative as you can see here on the screen. So what we do is we apply the power rule again to get the second derivative. So we can see here that it is a pretty straightforward linear function of minus 6x plus 12. So we can then simplify the equation to get x equals to 2, which is our inflection point or the critical point for the concavity. So by using a table and then substituting points in each interval, we could see where f of x is concave up and concave down. So we could see that it is concave up when it is less than 2, and it is concave down when it's greater than 2. So then we could just sub in x equals to 2 to find the inflection point. So we have another point on our graph to sketch. So by substituting it into the original function, we get 2, -2. So by adding this onto the graph, we can get a general sense of what this graph would look like using the inflection points and the concavity. So this is a rough sketch of the curve, and you can see that it is concave down all the way until 2, and then it is concave up for the rest of the function. So that is how we sketch the graph for this graph here. So I'm just going to go to the second function that we are supposed to sketch, which is a rational function, which is x over x squared plus 1. So doing the same process, I'm just going to go over the x, y intercepts, asymptotes, and then everything after that. So firstly, we're going to find the y-intercept, since that is the most obvious thing. The x-intercept is less so. So to find the y-intercept, it's pretty straightforward. We just substitute x equals to 0 into the function, and we get a value of 0. So since it both intersects the origin, it is both the x and y-intercept of f of x. So believe it or not, like as we can see, there are no more obvious x-intercepts. So we could just assume that there are no more. And believe it or not, there are no more x-intercepts on this graph. So as you can see here, the graph we have so far, we just plot the point 0, 0, as you can see on the chart we have. So for the asymptotes, we just analyze the f of x to see what the horizontal and vertical asymptotes are. So since the degree of the denominator is larger than the numerator, because the denominator degree is 2 and the numerator degree is 1, we know that the horizontal asymptote is equal to y equals to 0 at the endpoint. So when it approaches infinity, if we take the limit, it would be equal to 0 when it approaches both positive and negative infinity. So we then look at the denominator to see if there are any vertical asymptotes, and since x squared plus 1 does not intersect the x-axis, there are no zeros, there means that there are no vertical asymptotes, because the denominator will never be equal to 0. Therefore, f of x will never be undefined. So now that we know what the asymptotes are, we can then use this, we can look for the intervals of increase and decreasing for f of x. So as we per usual for the previous function, we just take the derivative. So for this one, we use the quotient rule to speed it up. So we can see, we just plug it into the general algorithm formula, and then we just simplify the equation that we have. So the first derivative of f of x in this situation would be negative x squared plus 1 over x squared plus 1, and then this would all be in squared brackets. So then to find the critical points, we just make the derivative equal to 0, and then we solve for that. So since we know that the denominator in this function as well will never be 0, because like any value, because the original function x squared plus 1 will always be a positive and non-zero. Since the square root of that will always not be 0, we know that we could just disregard the denominator. So essentially, we could just look at the top function minus x squared plus 1 and see when that equals to 0. So as a result, we see that x squared equals to 1, and then the critical points we have are x equals to 1 and x equals to -1 for the derivative. So using that information, we can create a table of values to see when it is positive and negative, to see when the function is decreasing and increasing. So we could see that it is decreasing when it's less than 1, increasing when it's in between -1 and 1, and then when it's greater than 1, it's decreasing again. So we know that as a result, there is a local min at x equals to -1 and a local max at x equals to 1. So substituting these points into the equation, we can then get the real local min and local maxes. So there's a local min at -1 and -0.5, and then we have a max at local max at 1, and then x is 1 and y is 0.5. So plotting that onto the graph, we could see the local max and local min, and then the x and y intercept, which goes through the origin. And then by adding the arrows, we could see where it's decreasing, increasing while keeping in mind the asymptotes of y equals to 0 on the graph at the endpoints. So next, we're going to look at the concavity. So we just take the derivative of the first derivative to get the second derivative. So using the quotient rule again, we get this equation, and we can simplify using algebra to eventually get 2x, and then in brackets we have x squared minus 3 over x squared plus 1 all over the power of 3. So as per usual, to find the concavity critical points, we just make f of the second derivative of x equal to 0. And since using our previous logic that x squared plus 1 will always be a non-zero positive number, since the cube of that will always be a positive non-zero number, we can disregard the denominator again when finding the 0 of this function, as you can see here. So we can just say that 0 equals to 2x, and then the inside is x squared minus 3 in brackets. So to solve this, we know that x is equal to 0 as one of the factors, and we know that x squared minus 3 is also equal to 0. So this simplifies to x squared equals to 3, and then we know that x is equal to both positive and negative square root of 3. Pretty easy to solve. So then, so now we can substitute this into the table of values. So we could see that when x is less than negative square root of 3, it is concave down since the second derivative is negative in that interval. It's positive in the next interval, negative, positive. So it's concave up from negative square root 3 to 0, and then it's concave down from 0 to square root 3, and then concave up again when it's greater than the square root of 3. So we can see that the inflection points are negative square root 3, 0, and square root 3. So we know that one of the inflection points is 0, 0, since that is one of our x and y intercepts. Continuing, we can substitute this into the function. So we could see that f of, by substituting in negative square root 3 and square root 3 into the function, we get the point square root 3 and square root 3 over 4 for the y value, negative square root 3 and negative square root 3 over 4 as the y value for the second point, and then 0, 0 as our last inflection point. So using all this information, we can finally sketch the curve. So we can plot the last two inflection points, plus keeping in mind that 0, 0 is an inflection point, to finally sketch out the graph. So as you can see, this is what it looks like. So we can see the asymptotes, the inflection points, and the local max and mins of the graph in this beautiful diagram here. So this concludes my curve sketching video. I hope you found it informative, and you can use this information to sketch your own curves of any function that you like if you can find the derivative of it. Thank you for watching.